Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
We're starting today with a pretty cosmic mandate, really, trying to find our closest Earth-like neighbors out there. And for this deep dive, we're looking into the future of space exploration, specifically at the machine designed to do just that, the Habitable Worlds Observatory. You'll hear it called HWO. Now, HWO is slated to be the next great observatory, following in the footsteps of giants like Hubble and Webb. But it has this incredibly specific central mission. It needs to analyze the atmospheres of at least 25 exoplanets, Earth-like ones, searching for biosignatures, basically signs of life. For a long time, the main strategy for HWO has really hinged on using an extremely powerful coronagraph. That's the specialized tool designed to block out the overwhelming light of a star, so you can actually see, hopefully, the faint little planet orbiting next to it. But here's the snag. Finding 25 worlds like that, especially when you don't even know for sure where most of them are hiding, that's a massive targeting problem.
It absolutely is. It's an issue of, efficiency and just sheer astronomical legwork. You could waste so much time pointing at the wrong places. And that difficulty, that strategic challenge, is exactly what Fabian Malbed and his colleagues are tackling in some new research. They're proposing that HW needs a bit of an upgrade, really. A powerful secondary instrument. One that could, frankly, revolutionize how HWO picks its targets for that crucial atmospheric analysis. Yeah, the big idea is adding a cutting-edge, super high-precision astrometry instrument to HWO's toolkit. And this isn't just like a minor tweak, it's a genuine leap in capability. If they do this, this instrument could potentially identify confirmed Earth-sized planets orbiting hundreds of nearby stars. Think about that. It would instantly feed the HWO coronagraph this, perfectly curated list of prime targets.
Okay, wow, let's unpack that straight away because, the implications there are pretty stunning. So this add-on dramatically boosts HWO's chances of hitting its main goal, finding those biosignatures, obviously. But you're saying it also gives us this remarkable, almost separate scientific bonus, that this incredibly precise planet hunter could actually double as a tool for cosmology, helping us map, maybe even solve one of the biggest riddles out there, how cold dark matter, CDM, is spread out.
Precisely. That's the unexpected twist. So for you listening, what we'll do in this dive is unpack the amazing tech precision needed for this. We're talking measurements down to half a microarc second. Just incredibly fine. We'll explore why that jump in sensitivity is so critical, the kind of engineering tricks that might make it possible, and what discovering all these planets and potentially mapping dark matter could mean for understanding our place in the cosmos and the universe's basic structure.
All right, let's start with HWO itself and its core job. It's a biosignature hunter, fundamentally. That means it needs to gather light from a planet potentially dozens of light years away, break that light down, and look for the chemical fingerprints of things like oxygen, methane, water vapor, things that could indicate life. And doing that takes a long time. Hours and hours of telescope time focused on just one single target. So picking the right targets efficiently, that's everything.
It really is. The coronagraph, as amazing as it is, needs good intel beforehand. It needs to know exactly where to point and ideally know the planet's orbit pretty well so it can track it effectively. And that leads us right into this significant gap in what we currently know about planets right here in our own stellar backyard. Just think about the stars within, say, 65 light years of Earth. That's our immediate cosmic neighborhood, right? These are prime candidates for HWO to look at.
Yeah.
But of the sun-like stars in that local bubble, we currently only know of planets orbiting about 12% of them.
Only 12%. And that low number isn't even the most critical part of the story, is it?
No, not at all. The really crucial detail is the kind of planets we've found so far around those nearby stars. Every single one of the confirmed planets in that local 65 light-year zone is a gas giant. We're talking worlds like Jupiter or even bigger. As of today, we haven't confidently identified a single rocky, Earth-sized exoplanet orbiting a nearby sun-like star. Not one.
Right. So let me just make sure I'm getting this straight for everyone listening. In this huge volume of space right around us, a space where we assume there should be plenty of smaller, rocky worlds, our best technology so far just hasn't been able to confirm any. It almost sounds wrong.
It's purely a function of our instrument's limitations. not necessarily a reflection of what's actually out there. It doesn't mean those Earth-sized worlds aren't there. I mean, all our theories of planet formation suggest they should be pretty common, actually. It just means the signals they produce, whether it's their reflected light or their gravitational tug, are currently getting drowned out by the noise. If you're trying to spot a tiny firefly right next to a giant searchlight, your camera needs incredible contrast and stability. Same idea here.
And that brings us squarely to this precision problem and the limits of our current best tool for this kind of work, the Gaia Space Observatory. Gaia's been amazing for mapping stars in the Milky Way, absolutely revolutionary, but for finding these tiny Earth-like worlds nearby, it kind of hits a sensitivity wall.
Gaia really is the gold standard for current astrometry. It measures the positions and movements of stars with phenomenal accuracy. But its absolute best precision, its limit, is around 20 to 30 microarc seconds. We usually write that as ICE.
Okay, 20 or 30 microarc seconds. That sounds incredibly tiny already. Why does that still fall short for finding an Earth twin? What's the physical scale here that we're missing?
Well, to grasp the challenge, you need to visualize the star's actual movement, its wobble. See, when a planet orbits a star, they both actually orbit a common center of mass. It's called the barycenter. Now, a really massive planet like Jupiter makes our sun move quite a bit. It pulls the sun around in a loop that's, about 2 million kilometers across. Even from 65 light years away, that's a relatively large angular displacement on the sky. It's something Gaia can measure, and that's why Gaia is great at finding gas giants. Okay, but now picture an Earth-mass planet orbiting a sun-like star. That tiny planet only makes its star wobble by maybe a few thousand kilometers, let's say under 10,000 kilometers over its whole orbit. Now translate that tiny physical movement into an angle on the sky, as seen from 65 light years away. That angular shift, the wobble we need to detect, it works out to be less than 1 microsecond.
Okay, so Gaia's best measurement, 20 to 30 ohms, is just way too coarse. It's like trying to measure something a millimeter wide with a ruler marked only in centimeters. We're hunting for a wiggle that might be, say, 30 times smaller than the inherent error, the noise level, in our current best instruments.
Exactly. That 20 to 30 ohms level is effectively the noise floor of today's technology for this specific task. And hiding beneath that noise floor, we think, are potentially hundreds of habitable Earth-sized worlds right next door. So the only way to really enable HWO's primary mission to give it those targets is to drastically lower that noise floor.
Right. So if the coronagraph is the tool for the deep dive, the detailed atmospheric sniffing, then astrometry, this wobble measuring technique, sounds like the perfect tool for the initial survey, for finding the worlds and figuring out their basic properties first. Can you give us a quick, clear definition of astrometry again, specifically how it helps us find exoplanets?
Sure. At its heart, astrometry is simply the science of measuring the precise positions and motions of stars over time, very accurately. When we apply it to finding exoplanets, we're looking for that tiny, repetitive, periodic shift in a star's apparent position on the sky. That shift is caused by the gravitational pull of an orbiting planet, tugging the star back and forth as they both orbit that common center of mass, the barycenter. We're basically tracking the star's side of that orbital dance.
And the beauty of it is the size of that wobble directly relates to the mass of the planet doing the tugging, right? Bigger wobble, bigger planet mass.
Exactly right. And that's the huge advantage of astrometry. Because that gravitational relationship is so well understood based on physics, if you can measure that wobble with extremely high precision, you can calculate the exoplanet's entire orbital solution, its orbital period, how far it is from the star on average, the semi-major axis, even how elliptical its orbit is. You basically get a complete map of its path, which tells you exactly where that planet will be at any given time. And that's absolutely critical for pointing the coronagraph later on.
Okay, so that's the practical benefit, better targeting, knowing where to look. Makes sense. But you also mention a fundamental scientific advantage, something that other main planet-finding methods, like the transit method or radial velocity, can't quite deliver with the same certainty.
Yes, and this is key. Astrometry allows you to determine the exoplanet's absolute mass, not just a minimum mass, but its actual mass. See, the radial velocity method, which measures the star's wobble towards and away from us, only gives you a minimum possible mass for the planet. That's because the signal depends on the tilt of the planet's orbit relative to our line of sight, and usually we don't know that tilt precisely. Astrometry, though, measures the side-to-side wobble on the sky. That measurement directly gives you the true, unambiguous mass of the planet. And why is knowing the true mass so important? Well, think about HWO's goal, finding life. To assess if a planet could host life, we first need to know if it's even rocky, right? If you can combine that absolute mass from astrometry with the planet's radius, which you might get if you're lucky and the planet also happens to transit passing in front of its star, from our view, then mass plus radius gives you density.
And density is the killer metric. It's what fundamentally tells you if you're looking at a dense, rocky world like Earth or Venus, or a puffy, low-density gas or ice giant like Jupiter and Neptune, which are, let's face it, much less likely places to find life as we know it. So astrometry provides that foundational piece of the puzzle for figuring out if a planet is even potentially habitable in the first place.
Okay, so it all comes back to the main challenge, getting sensitive enough to measure that incredibly tiny wobble from an Earth-mass planet. Gaia, our current best, is stuck at around 20-30 oins. What's the leap in precision that Dr. Malbit's proposal is calling for? How much better do we need to be?
The instrument they're suggesting aims for an operational precision of, let me get this, 0.5 microarc seconds.
Half a microarc.
Sure.
Wow. Okay, just comparing that to Gaia, which is already state-of-the-art. You're talking about making this new instrument on HWO something like 400 to 600 times more sensitive than Gaia. That's not just like the next step up. That's like skipping 2 whole generations of technology. It completely changes the game for HWO's mission.
It really does. Just to give you a sense of scale for 0.5 targets, that's roughly the angular size of a single human hair viewed from about 500 miles away. It's an unbelievably fine measurement we're talking about making from space. And achieving that level of sensitivity, that 0.5 targets, is the absolute key. It's what unlocks potentially hundreds of new exo-Earth candidates right in our solar neighborhood. It means HWO's giant coronagraph doesn't have to waste precious time searching blindly or inefficiently. Instead, it gets handed this highly optimized, pre-vetted list of confirmed targets, complete with their masses and orbital details, making it much, much easier to efficiently tick off that primary mission goal, finding those 25 biosignatures.
Okay, boosting precision by a factor of, say, 400 or 600. That obviously means you have to overcome some equally huge technical challenges. If doing astrometry at 0.5 highs was easy, presumably we'd have done it by now. So what's the main weakness? What makes these astrometers so prone to error that we need to fix?
Well, even out in the relative stability of space, astrometers are inherently susceptible to what we call systematic errors. You're trying to measure an angular shift on the sky that's smaller than the width of a virus, right? So every tiny physical imperfection in the instrument itself, whether it's in the detector chip, tiny misalignments in the mirrors, slight changes due to temperature, all these things can combine and create noise that swamps the signal you're looking for. The main offenders are usually imperfections in the detector and just thermal instability. The sensor, typically a CMOS chip like in your phone camera but much more advanced, isn't mathematically perfect. The pixels aren't all identical squares. They have tiny variations in how sensitive they are, their exact size, their electrical behavior. That's due to the manufacturing process, and it's called fixed pattern noise. Now, if that sensor shifts even minutely relative to the incoming starlight, or if its temperature fluctuates by even a tiny fraction of a degree, those built-in imperfections create errors in your position measurement. And those errors very quickly add up and overwhelm the sub-microarc-second signal you're desperately trying to detect. That inherent instrumental noise floor is basically why we've been stuck around that 20-30 ounce limit for so long.
Okay, so to break through that barrier and actually hit 0.5 noise, Malbit's team is proposing a kind of 2-pronged attack, right? A strategy to cancel out both those predictable, systematic errors from the hardware itself and also the unpredictable, random noise from the environment. Let's start with the first part, the clever bit of technology, the detector calibration unit, or DCU. What does that do?
The DCU is a really neat piece of engineering. It's designed specifically to tackle that fixed pattern noise problem on the CMOS sensor head-on. So you've got your sensor, which is basically this grid of millions of tiny light-collecting pixels. The DCU generates a set of extremely precise, stable reference patterns. Think of them like light and dark interference fringes or a super high-resolution grid pattern. And it projects these known patterns directly onto the face of the CMO sensor itself while you're observing.
Ah, okay. So it's like shining a perfect, unchanging calibration ruler directly onto the detector every time you take a picture.
Exactly. That's a great analogy. The DCU allows the system to isolate and map the precise physical location and the specific response characteristics of every single pixel in that detector array. And this calibration isn't just done once, it's done constantly or very frequently. It effectively corrects for all those tiny pixel-to-pixel variations, any slight geometric distortions introduced by the telescope's optics, and even tiny changes in the detector's own internal shape or geometry caused by minute thermal expansions or vibrations. What it does, basically, is create a perfectly stable internal coordinate system right on the detector itself. So when the light from the target star hits that sensor, the DCU calibration ensures that any measured shift in the star's apparent position is a real angular movement due to its gravitational wobble. And not just some artifact caused by the telescope hardware warming up by 1,000th of a degree or a pixel behaving slightly differently than its neighbor. It aims to drive that systematic error contribution down to almost zero.
Okay, that sounds like it tackles the predictable flaws in the hardware pretty effectively. But even with a perfect DCU, you're still going to have some residual fuzziness, right? Random errors from things like stray background light, maybe a cosmic ray, hitting the detector, tiny thermal jitters. So this requires the second ingredient in the recipe, basically statistical brute force. You need lots and lots of data.
You need a massive amount of data. The estimate they provide in the paper suggests that to really nail down the conformation of an Earth-mass planet and to average down all those random errors to achieve that overall 0.5 arrow precision goal, HWO would probably need to collect over 100 separate high-precision measurements of that particular star system.
And these aren't just 100 snapshots taken one after another, I assume. You need to spread them out over time to actually see the orbit.
Absolutely correct. These 100-plus measurements would need to be distributed over the course of HWO's planned operational lifetime, which is typically expected to be around 3 to 4 years. You need that long-time baseline to actually track the star through a significant portion, ideally more than one full cycle, of its gravitational wobble caused by the planet. That's how you confirm the orbital period accurately. And the reason for needing so many images, the statistics part, is pretty straightforward. Even the brilliant DCU can't stop every single random, unpredictable error, a stray photon here, a tiny vibration there. These are stochastic events. But the magic happens when you take 100 or maybe 150 of these individual measurements. The central limit theorem from statistics starts to work in your favor. Random errors are, by definition, random. They scatter. So if one measurement happens to have a random error that nudges the star's measured position slightly to the north, it's likely that another measurement taken later will have a roughly equal and opposite random error that nudges the position slightly to the south.
Right, so by combining and averaging all those hundreds of measurements together, you effectively force those random plus and minus errors to statistically cancel each other out over the long run, leaving behind only the consistent underlying signal, that tiny, stable, repeatable gravitational wobble of the star caused by the planet.
That's exactly the rationale. It's this combination, this marriage, of highly sophisticated, real-time technical calibration, that's the DCU, with the sheer power of statistical averaging from taking lots and lots of pictures. That gives us confidence we can actually stabilize the final result down to that incredibly demanding 0.5 A's of precision level. It transforms a mission initially conceived around just a coronagraph into potentially the definitive surveyor of nearby planetary masses as well.
Okay, now we pivot to the part that, for me, really elevates this whole proposal. It goes beyond just making HWO better at its main job. The idea that an instrument fine-tuned to measure a star wobbling by just a few thousand kilometers could also give us real leverage on one of the universe's biggest mysteries. Cold dark matter. That's pretty amazing.
It is a truly remarkable example of how pushing the technological envelope in one area of science can suddenly, unexpectedly, unlock brand new capabilities in a completely different field. HWO's proposed astrometer, if built to this 0.5 AN spec, could provide crucial observational data to directly test the standard model of cold dark matter. Specifically, it could help resolve a long-standing puzzle about how dark matter is actually distributed right in the centers of galaxies.
Right, and this gets into the famous cusp versus core debate, doesn't it? If dark matter is cold, meaning it moves slowly and mostly non-interacting except through gravity, which is the standard CDM picture. What should happen to it near the superdense center of a galaxy? What does theory predict?
The standard CDM theory is pretty unequivocal on this. It should form a cusp. Because dark matter particles in this model only really feel gravity, they should just keep getting pulled deeper and deeper into the galaxy's gravitational well. This process should cause the density of dark matter to continuously increase the closer you get to the very center, creating a really steep, sharp spike in density right at the core, like a pointy cusp.
Okay, so theory predicts this sharp density peak. But what do our observations actually show us? Especially when we look at smaller dwarf galaxies where the dark matter signal is often clearer, less mixed up with normal matter.
Well, that's where the tension arises. Observations, particularly from studying how stars orbit in the outer parts of galaxies, and especially in these smaller dwarf galaxies, they frequently suggest something different. The data often indicates that the dark matter density profile tends to flatten out in the very center. Instead of that sharp cusp, we seem to see a core, basically, a region where the dark matter density is more or less constant, or at least doesn't spike up dramatically right at the galactic heart.
So theory predicts a steep point Observation suggests more of a flat plateau in the middle. That's a pretty significant disagreement. And the existence of these apparent cores implies something's going on that isn't in the simplest CDM model, right? Either our assumptions about dark matter are wrong, or something else is messing with its distribution.
Exactly. If these cores are real and common, it means something must be acting to sort of smooth out or push that dark matter away from the very center. What could it be? Well, one possibility is astrophysical feedback from normal matter, things like massive bursts of star formation and powerful supernova explosions. These events can violently expel gas and energy, potentially pushing the dark matter outwards too, dynamically creating a core over time. Or maybe point to something fundamental about the dark matter particles themselves. Perhaps dark matter isn't completely non-interacting. Maybe it's self-interacting dark matter, or SIDM, where dark matter particles can actually collide and scatter off each other occasionally. That kind of self-interaction would naturally tend to smooth out the central density peak, turning a cusp into a core.
And this is where HWO's super precise astrometer comes back into the picture. We're not looking for a star's wobble anymore. We're talking about using that same incredible 0.5 VSO's precision to detect the subtle gravitational effects of those predicted dark matter cusps themselves, if they exist. How does that work? How does measuring star positions help us see a dark matter cusp?
We'd use the phenomenon called gravitational lensing, or more specifically, gravitational deflection of light. Any concentration of mass, like the dense dark matter cusp predicted by CDM theory, will bend the path of light that passes near it. Now, we can't see the dark matter directly, of course, but we can see distant background stars or quasars whose light has to travel past or through these potential dark matter concentrations in nearby galaxies on its way to us. If a dense dark matter cusp is sitting there between HWO and some distant background star, the gravity of that cusp will slightly deflect the light from the background star. This deflection causes a tiny, tiny shift in the apparent position of that background star as seen by HWO. That predicted shift, caused by the lengthening effect of a standard CDM cusp, is incredibly small. Calculations suggest it's right around the level of, you guessed it, 0.5 microarc seconds. So only an instrument with the kind of precision being proposed for HWO's astrometer would actually be sensitive enough to reliably detect these minuscule deflections caused specifically by the presence of a dark matter cusp.
Ah, I see. So the logic is, if this astrometer looks at millions of background stars shining through the centers of nearby galaxies, and it consistently fails to find those telltale 0.5 theta-stick positional shifts that a cusp should produce, then that provides strong evidence that the cusps aren't there and the dark matter must be arranged in cores instead.
It would provide potentially definitive, clean observational evidence, yes. That kind of data, a null result across many targets, would really force cosmologists to seriously reevaluate the standard, simplest CDM model. It would lend powerful support either to alternative dark matter theories like self-interacting dark matter, or to models where astrophysical feedback processes are extremely efficient at flattening out the central densities. So this one instrument, born out of the very practical need to find nearby Earth-like planets, suddenly becomes this fundamental probe for understanding the distribution of dark matter and the very structure of galaxies.
It really is quite something. The solution to a tricky planetary measurement problem, potentially unlocking answers to a deep cosmological mystery. Now, this proposal sounds incredibly powerful, almost essential, given these potential twin scientific payoffs, better exoplanet hunting, and insights into dark matter. But space missions are notoriously complex, incredibly expensive, and take decades to plan and build. So let's put this idea into context a bit. How developed is this concept? Is it brand new, or does it have some history? And why does it make sense to try and tack it on to HWO now?
Well, that's a good point. And the idea is actually highly mature, technically speaking. It didn't just spring up out of nowhere for HWO. Dr. Malbit, who led the recent paper, was also a key figure behind a much earlier, very detailed mission proposal called Theia.
Theia, I remember hearing about that. That was basically envisioned as a dedicated space telescope whose entire purpose was going to be ultra-high precision astrometry, right? Using essentially the same core technology concept.
That's exactly right. Theia was designed from the ground up as a standalone mission, completely separate from the lineage of the great observatories like Hubble, Webb, or HWO. The Theia team spent years meticulously developing the concept, working through the incredibly demanding error budgets, figuring out how to control systematic errors, and designing the specialized hardware needed, including crucial calibration systems like that detector calibration unit, the DCU we discussed. Now, ultimately, Theia wasn't selected by the funding agencies to move forward and actually launch, but all that detailed engineering work, the simulations, the technical solutions, that knowledge base still exists and is highly valuable.
Okay, so if you look at it strategically then, since the really hard groundwork for achieving this kind of super precision astrometry has largely already been done for Theia, it seems incredibly logical, maybe even efficient, to try and incorporate that already developed capability into HWO. You avoid the huge cost and complexity of launching a whole separate, dedicated mission like Theia was planned to be, while at the same time you significantly boost HWO's ability to achieve its own primary goal. Kind of a win-win.
It really does look like a way to maximize the scientific return on investment for a single major flagship mission like HWO. I mean, any instrument that can quickly and definitively find and confirm potentially hundreds of Earth-mass planets right in our solar neighborhood. That directly makes HWO's main job, getting those 25 biosignatures, far more achievable within its likely mission, lifetime, and budget. It feels like perhaps the smartest way to leverage all that prior R&D investment from the Theia effort and, frankly, reduce the overall risk for HWO's core science.
However, we should probably ground ourselves, and you, the listener, in the actual timeline here. HWO isn't launching next year, or even this decade.
Oh, far from it. HWO development is still very much in the early study and planning phases.
Yeah.
Serious hardware construction and detailed engineering work aren't really expected to kick off in earnest until sometime in the 2030s. And the most optimistic launch window for HWO itself is probably somewhere in the early to mid-2040s. We're talking 20 years out, maybe more. But interestingly, that long lead time is actually a major advantage for this astrometry proposal. It means there's still plenty of time, well over a decade, potentially to fully finalize the instrument design, build and thoroughly test prototypes of things like the detector calibration unit, and figure out how to integrate the whole astrometry package smoothly into the larger HWO observatory architecture without causing major delays or disruptions to the primary coronagraph instrument, which is still the centerpiece.
Right. So the underlying science case seems solid. The core technology is apparently quite mature thanks to the earlier Theia work, and the long HWO timeline actually provides a feasible window for implementation. So the final decision really comes down to the HWO project managers, the scientific advisory committees, and ultimately the funding agencies like NASA. It sounds like a classic strategic decision. Do you stick rigidly to the original, highly focused mission plan for HWO centered on the coronagraph? Or do you allow the mission's scope, its scientific ambition, to grow a bit to incorporate this incredibly powerful dual-purpose astrometry capability given the groundwork already laid?
It really is a choice between perhaps maximizing the potential scientific discovery space versus maintaining programmatic simplicity and sticking to the original baseline. Integrating the astrometer undoubtedly adds complexity to the overall instrument package and the mission operations. There's no denying that. But the potential scientific payoff, having hundreds of confirmed exo-Earth masses to feed the coronagraph, plus getting unique observational constraints on the nature of dark matter, that payoff is arguably multiplicative. It could be huge. It's definitely a major decision point that will likely shape HWO's ultimate scientific legacy long before it ever leaves the ground.
It certainly seems to shift the perception of HWO, doesn't it? From being primarily a specialized machine for analyzing atmospheres to becoming potentially a much more versatile foundational observatory for broad areas of space physics as well. Well, this has been a really fascinating look into the kind of high-stakes planning and technological innovation that goes into shaping the next generation of big space science missions. We started with this fundamental need, just finding a better, more efficient way to locate those small, rocky worlds that HWO is ultimately designed to study up close. And that led us down this path, exploring an incredibly complex technological leap, combining that sophisticated detector calibration unit with the need for maybe over 100 statistical measurements, all just to reach that almost unbelievable 0.5 microarc-second precision target.
And then we discovered this amazing bonus, that this hyper-precision, initially conceived just for measuring planet masses accurately, it simultaneously gives us this completely new, powerful way to probe the universe on a much grander scale. It provides exactly the kind of leverage needed to observationally test competing theories about how cold dark matter behaves in the hearts of galaxies, potentially resolving that cusp versus core puzzle that's been nagging cosmologists for years. So this proposed astrometer, it really isn't just some minor add-on. It feels like it could fundamentally shift the scientific identity of the Habitable Worlds Observatory. It potentially transforms it from being a highly specialized, though important, coronagraph mission into more of a foundational dual-purpose powerhouse for both incredibly precise exoplanet characterization and fundamental deep space physics. It just seems to maximize the potential science you get out of one enormous public investment.
And thinking about that dual-use potential, If one instrument developed primarily to measure a star moving just a tiny bit because of a planet 65 light years away, if that same instrument could also potentially help resolve one of the deepest mysteries we have about the fundamental structure of the entire universe, it really prompts a final question for you, the listener, to maybe mull over. As we continue to pour billions into developing ever more sensitive, ever more precise scientific tools for space, what other profound, perhaps completely unintended discoveries might already be lurking, waiting to be made, within the designs and development pipelines for missions that haven't even launched yet? Often, the biggest scientific leaps seem to happen almost by accident, when instruments built for one very specific purpose turn out to have an even grander application in a completely different scientific domain we hadn't anticipated.
It's that kind of beautiful, unforeseen synergy that often drives scientific discovery forward in surprising ways.
Absolutely. Well, thank you for joining us for this deep dive into the exciting future of space exploration and the potential of the Habitable Worlds Observatory. We'll catch you on the next one.